Hello and welcome to my talk. I'm Alex Steiger, and today I'll be presenting our work on computing the union of cubes and fat boxes in 3 dimensions. This is joint work with my advisor, Pankaj Agarwal at Duke. In this problem, we're given a set of n axis-aligned cubes in 3 space, which will denote their union by U, and the complexity of the union, counting its number of vertices, by k. Now, k ranges from constant up to quadratic in n, and is order n when all the cubes have the same size. So the problem that we consider is to compute the features of the union, that is, its vertices, edges, and faces. And ideally, we would achieve this in n log n plus k time. We'll note that there's this closely related problem, the so-called Clee's measure problem, wherein we want to compute the volume of the union as opposed to its features. So we first note that both of these problems have been considered extensively over the years, and we'll start with the results in the plane. So here we're given n axis-aligned rectangles with no restrictions on the side lengths. Bentley showed that you can compute the area in n log n time, and if you extend those techniques, you can get n plus k times log n to compute the union. Shortly after, Gouting followed by Wood gave different algorithms to compute the union in only n log n plus k time. Now coming to 3D, with still no restrictions on the side lengths of the input boxes, Bentley's techniques give you n squared log n to compute the volume of the union. This was later improved in the breakthrough by Overmars and Yap, achieving roughly n to the 3 halves. Finally, Chan recently indeed achieved exactly n to the 3 halves time. When it comes to computing the union of boxes in 3 dimensions, one might extend the results of Overmars and Yap and achieve an additional plus k log n factor. Now, all of these results lead to the question of, can we improve on these runtimes when the boxes are so-called fat, or the side lengths of the input boxes are similar to one another? And so we arrive at the setting that we consider. So here, to compute the volume of the union of cubes now, Agarwal et al. Showed that indeed n to the 3 halves can be beaten, and was improved down to near linear in n recently. For computing the union itself, very recently, just this year with Mika Sharir, we showed that a randomized algorithm can compute the union of unit cubes in near linear time, but was not ruled out whether or not n polylog n plus k could be achieved for arbitrary cubes as opposed to only unit cubes. In this work, we show that indeed the union of cubes can be computed in roughly n polylog n plus k time. Our algorithm can be made a little more efficient if we have a guarantee the input cubes are either all the same size or if they have so-called bounded depth. This is where any point in 3 space is contained in only a constant number of the input cubes. And if both of those conditions are satisfied, that is, unit cubes with bounded depth, then the desired n log n plus k runtime can be achieved. In the remaining time of this talk, we're going to discuss our first result as follows. Before we begin, we'll note that we're going to focus only on reporting the vertices of the union as opposed to also its edges and faces. Reporting the edges and faces is relatively straightforward in comparison to the vertices. So we'll first make the observation that every union vertex is defined by the intersection of 3 cube faces. In particular, one face is horizontal. So we'll restate the problem as reporting for each horizontal face of the cubes, the union vertices that lie on it. Of course, some faces might not have any vertices on it. Our approach to this is to start with a horizontal plane H below all of the cubes, which we will sweep upwards. And as we perform this sweep, we're going to monitor its cross-section of the union that lies on the plane. So in particular, when H reaches the bottom face of a cube, the square projection of that intersected cube is now being inserted into the cross-section. This cross-section and how its vertices change corresponds to the 3D union vertices. that lie on that face. So for example, if we look on the figure on the right, starting at the bottom, the plane first crosses over the bottom face of the red cube, and the cross section now consists of only that red square. And its four vertices correspond to the four vertices of the 3D union. As the plane continues to reach up, it eventually crosses through the bottom face of the blue cube, and that blue square is inserted to the cross section. The differences in the vertices of the cross section due to the insertion of this blue square again correspond to 3D union vertices on this blue face. In particular, the white vertices are newly created when that blue square was inserted, whereas the only black vertex is an old vertex of the cross section before the insertion, which is no longer because it is contained and covered by the blue square. Thus, what we've done is reduce the problem from computing these 3D union vertices on each of the horizontal faces of cubes to now reporting the changes in the cross-section as the sweeping plane begins and stops intersecting the cubes during the sweep. In the remaining time, we'll be discussing how we maintain this 2D cross-section in a way that supports insertions and deletions of squares as this plane sweeps through those cubes. So from now on, we're going to be focusing on the process of inserting a square into the 2D cross-section as opposed to both insertions and deletions, with the reason being that the deletion is distinct but similar to insertions. The idea is similar to the previous reduction from 3D to 2D. We're going to be sweeping a line segment through the inserted square, call it Q, and we want to monitor the 1D cross-section of this line with the existing squares. And when that cross-section changes, that corresponds to a vertex to report, and we report those vertices. The sweep has to take time proportional to the number of changes to the 2D cross-section and not the total number of squares that intersect Q. So as we can see on the figure on the right, there are 4 vertices to report on the interior of Q, but there can be any number of squares that intersect Q without contributing any changes. So we will be able to achieve this, but heavily relying on the fact that the input to the original problem are 3D cubes whose projections are these squares in 2D. So before getting to the finer details of this line sweep, we're going to introduce a core component of our algorithm, namely a quad tree. And so this is a hierarchical decomposition of the plane constructed over a point set. In this case, our point set is the set of projections of the vertices of the input cubes down onto the plane. So every node in this quad tree is associated with a square cell. We call this RU. In particular, the root node of the quad tree, its cell contains all of the points. And then any node with more than one point in its cell is further divided into 4 cells and its 4 children. And then of course, any leaf node contains either 0 or 1 point in its cell. For the purposes of this talk, we will assume that the projection of the cube's vertices have so-called bounded spread, which is to say that the ratio of the distance between the farthest pair of points and the closest pair of points is polynomially bounded in n, the number of cubes. With this assumption, we have that the quad tree has height log n. Now, before we discuss how to use this quad tree T during our algorithm, we next introduce some useful terminology. In particular, we'll classify squares intersecting a quad tree cell to be either long or short. So we'll say that a square A is called short for a quad tree cell B if B contains a vertex of A, and otherwise A is long. In the example on the right, the short squares are red and the long square is blue. Now, it's worth mentioning here that because we're only ever inserting squares to the cross-section, given that they are the projections of these 3D cubes, we don't have something like what is shown in the figure on the right now. We have this thin rectangle that is cutting across the quadricell without containing an edge. We'll point out that the blue long square does contain an edge of the quadricell, and indeed, any square that is long for the cell would contain one of the cell's edges. Our following techniques are going to rely on the non-existence of these thin gray rectangles. With these definitions of long and short squares in hand, we can now state the following. For our square Q to be inserted to this 2D cross-section, it is partitioned by cells of log n nodes of the quadtree, and we'll call these nodes pi q. And the cells of these nodes come in two different types. So the first type is where our square Q is short for the quadricell, and that node is a leaf, or Q is long for the quadricell, but short for the cell at the node's parent. So when we're inserting square Q into the 2D cross-section to report the vertices, we're going to do it locally within the cells of these log n nodes pi q. So in the following, we're going to give some details as to how we do this for specifically quadricells that Q is long for. The other case where Q is short for the quadricell is fairly straightforward. So to report the changes within the quadricell RU, the first observation we make is that within the quadricell, the existing squares in the cross-section are all, of course, either long or short at RU. In particular, if we consider the long squares, those contain some edge of RU, as depicted on the right, and thus the complement of those long squares is a rectangle contained in its interior, and we'll call that rectangle rho U. So the significance of this rectangle rho U is that all vertex changes in the cross-section as a result of inserting square Q, they all lie in both Q as well as in rectangle rho. Hence, we set QU to be the intersection of Q and rho U, and then we will perform our sweep through QU to report any vertex changes. So first things first, we know that any existing square of the cross-section that intersects QU must be a short square because the boundary of QU is defined by the long squares. So we're going to further classify these short squares by their number of vertices that lie in the quadricell. So we'll call them corners if exactly one vertex lies in the quadricell. Otherwise, we'll classify them as floaters, which have either 2 or 4 of their vertices lying in the quadricell. Corners will be green and floaters will be orange in this example. So to ultimately report the vertex changes of the cross-section within QU, we're going to sweep a line L from, say, the top edge of QU down through these short squares to its bottom edge. The sweep line, we're going to move atomically from floater edge to floater edge and not stop at the corner edges. The reason for this discrepancy is outside the scope of this talk, but we will say it's tied to the fact that floaters, because they are smaller than the quadricell, they are smaller than the square Q being inserted, but this may not be true for the corner squares. These corner squares can be arbitrarily large with respect to both the quadricell and to Q. So let's go through this example to illustrate how we actually implement this sweep line process. As we sweep our line L downwards, we maintain the floaters being intersected by that line L in a data structure. This is being used to represent the 1D cross-section of those floaters on the line. We also use the data structure to detect and report the changes of the vertices of this 1D cross-section, as seen here in this example. So here, the blue interval is the projection of the first floater, and its white endpoints correspond to 2D vertices of the 2D cross-section within QU. Moving the line down to the next floater edge, the cross-section on L now includes the red interval. The right endpoint of the red interval is a new vertex of the cross-section, shown to be a white 2D vertex. And on the other hand, the right endpoint of the blue interval has now become covered by the red interval, which corresponds to the black 2D vertex. Now moving the line to the bottom of the first floater, the line stops intersecting this floater, and hence we delete the blue interval from the 1D cross-section. Its left endpoint no longer remains a vertex of the cross-section, and the left endpoint of the red interval now becomes a vertex of this 1D cross-section. And so these endpoints correspond to 2D cross-section vertices shown. Next, the line reaches the bottom edge of the second floater, and the 1D cross-section becomes empty as line L is no longer intersecting any floaters. As such, the two endpoints of the lone red interval being deleted, those correspond to 2D vertices, which are shown in black. As mentioned earlier, the next step is to sweep to the next floater edge, and hence we're going to be skipping over those green corner edges in the process. So those on L at the next position, the corner squares do intersect L, but they don't interact with the 1D cross-section of the new floater, namely the purple interval shown. So the endpoints of the purple interval belong to the 1D cross-section, and again correspond to 2D vertices, which we show in white. But we still need to report the green vertices that the line L skipped over. These are contributed by the corner vertices. And to report them, we use a different data structure which stores the corner squares. So at a very high level, the data structure is relying on this staircase-like structure that this union of corner squares has within the rectangle, as you can see in this example. Finally, we move the sweep line L to the bottom of the floater, and we report the green vertices in the slab between this position of the sweep line and the previous position, using this data structure over these corner squares. Then we report the vertices that lie on L itself, and unlike the previous cases for L, the union of the corner squares is interacting with this purple interval of the floater. So the left endpoint of this purple interval ceases to be a vertex of the 1D cross-section, as L no longer intersects any floaters. And a green vertex, as shown here, is defined by the intersection of this green union of corner squares with the purple interval. Now that we've gone through that example, let's speak more generally about how much time is spent during the sweep. So in particular, when the sweep stops at a floater edge or the bottom edge of QU, we report the vertices that lie on that line in order log n plus k time. And these are the black and white vertices as shown in the previous example. This is using the data structure of wood. Then, using the data structure of Agarwal, we can report those green vertices contributed by the corner squares between consecutive stops of the sweep at these floater edges. So this takes log square n time plus k, where k is the number of vertices being reported. And so this concludes our very high-level description of how we report these changes within rectangle QU. Next, we'll give a high overview of the runtime analysis. So let us recall that when we're inserting square Q, we take these log n nodes of the quad tree, call them pi q, whose cells at these nodes are partitioning Q. And within each one of them, we're doing a sweep. That was the algorithm we just described. So in a single cell, we spend log square n overhead plus log square n time for each time that sweep stopped, which occurs when we're sweeping over a edge of a floater. And then we spend constant time per vertex change. So summing up over the log n cells of pi q, we get an overhead of log cubed n plus fq times log square n, where fq is the number of floater edges swept over in total during the insertion of q, plus kq, where that's the total number of vertices reported as we insert q. Given that insertion and deletion roughly have the same runtime analysis, if we sum up over all of the insertions and all of the deletions, the total overhead we incur for these n operations is n log cubed n plus f log square n plus k, where k is the union complexity, and f here is the total number of floater edges swept over in all insertions and deletions of squares. So the crux of this runtime analysis is in showing that f can be bounded by n log n. And we'll note that proving this claim hinges on the fact that these cubes that we're inserting into a 2D cross-section, these belong to specifically cubes as opposed to, say, very thin boxes that have square projections. So plugging this bound of f equals n log n into the overall runtime above, we get the desired n log to the 3n plus k. And this concludes our overview of our main result. So to recap, the majority of our time spent was discussing our first result, which is computing the features of a union of 3D cubes in n log to the 3n plus k, where these features are its vertices, edges, and faces. The runtimes can be improved in two specific cases, and now we'll leave you with two open questions. So first, can we improve the runtime of our algorithm for arbitrary cubes down to O of n log n plus k? Second, can we improve upon the runtime from Overmars and Yap's techniques for d-dimensional cubes, for larger dimensions d? In particular, can we improve on n to the d over 2 plus k time in this case? And with that, thanks for listening.